Hello everyone. This course continues from the previous course on the working principles of automatic low-frequency load-shedding device. In our courses of power systems, relay protection, and secondary circuits, there are some basic requirements for each type of device. So, what are the requirements? For automatic low-frequency load-shedding devices, the first requirement is to be able to systematically remove loads in various operating modes and in the event of a significant power shortage, effectively preventing the system frequency from dropping below the danger point. The second requirement is that the load to be removed should be as less as possible to minimize the impact on users. The third requirement is that the device should operate reliably when the feeder line of the substation trips the faulty transformer, causing a voltage drop or even losing voltage. The fourth requirement is that the automatic low-frequency load-shedding device should not misoperate when low-frequency oscillation occurs in the power system. The fifth requirement is that the device also should not misoperate when the power system is interfered with by harmonics. Next, we will analyze the working principle of the automatic low-frequency load-shedding device. First, let us look at the process of the system frequency change. In the previous lesson, we introduced the action order of the automatic low-frequency load-shedding device, i.e., the levels or rounds, i.e., F1, F2, Fn, etc. As shown in the figure, at point 1, a large active power shortage occurs in this system, and at this time, the frequency drops to F1. At point 2, the first round starts, and after a certain time, delta T1 arrives at point 3. Where the position of point 3 removes a part of the users. This is the first calculation of the power shortage. Then, at point 3, after removing some users, if the power shortage is still relatively large, the first calculation does not get the value of the active power shortage of the system. The frequency will continue to fall, but at this time, due to the removal of part of the load, the power shortage has been reduced, so the frequency will continue to fall according to the curve in the figure of 3 to 4 instead of the curve 3 to 3. When the frequency drops to F2, that is 2.4, the second round starts. After a certain time delta T2 to the position of point 5, and then disconnects part of the user. Then, between points 5 and 6 of the system, active power shortage is compensated for. The frequency begins to rise along the curve 5 to 6, and finally, the frequency is stabilized at F2 infinity operation. Actually, the automatic low-frequency load-shedding device utilizes the principle of successive approximation. That is to say, it carries out calculations over and over again until it finds the value of the system's power shortage, but meanwhile, it also disconnects the corresponding users. That is, the process ends only when the system frequency is stabilized again or when there is a rise in frequency, generally after 5 levels rounds. The system frequency will be restored to the permissible frequency values. Next, we will look at the last problem, is to ensure that the device does not miss operation, but the device will miss operation due to several reasons. Then, we have to take certain measures. The first reason is that when the low frequency relay context jitter. Due to the sudden change in system voltage, it may cause load shedding device to misoperate. The measure taken is to add 0.1 to 0.2 seconds delay time to avoid this jitter. The second reason is that the automatic low-frequency load shedding device may misoperate before the rotating standby capacity of the system takes effect. The measures to be taken are also to add a certain delay time in the first few levels, or to reclosing when the frequency is restored to the rated value. The second reason is that load feedback can cause the misoperation. The specific reason is that the regional substation has some operations or during the transmission line reclosing, load and power supply will emerge. A short period splitting, then the kinetic energy of the rotating units in this regional load still feeds back the transmitted power for a short time, generating a voltage on the bus, which gradually decays and the frequency drops sharply, which will cause the low-frequency load shedding device misoperation. Then, the measures taken for this situation are current, voltage, sleep, and other blocking, and can also be corrected by automatic reclosing by frequency. The current blocking used is to connect the blocking relay to the main power incoming line or transformer, and its contacts are connected in series with the low-frequency relay contacts, so that when the power supply is interrupted, the current relay does not act and the device is blocked, which prevents misoperation. This blocking current must be less than the minimum load current to prevent error locking. Similarly, the voltage blocking is to connect the blocking relay to the same node voltage of the low-frequency relay, and its contacts should be connected in series so that when the power supply is interrupted, the voltage relay does not act blocking the device. The magnitude of the blocking voltage should ensure that the device cannot be blocked. When the bus bar is operating at the lowest voltage after the transmission line recovers power, generally the blocking voltage is 0.65 to 0.7 times the rated voltage of the bus bar. Sleep locking utilized the change speed of the frequency drop to the action frequency to distinguish whether the frequency drop is caused by system power shortage or by low feedback voltage, so as to judge whether the block or not. We concluded from years of practical experience, if the frequency drop rate is less than 3 Hz per second, it is considered to be the frequency drop caused by the system power shortage. If the frequency drop rate is greater than 3 Hz per second, it is considered to be the frequency drop caused by the load feedback. So, the condition for sleep blocking is that the change speed is 3 Hz per second. A final measure is to adopt automatic reclosing by frequency to correct it after the low-frequency load shedding device occurs misoperation using the reclosing device, that is, activated by the change speed of the frequency drop to the action frequency, which is a relatively effective remedy. This is the misoperation caused by load feedback and some measures to prevent it. Of course, in the actual use of automatic low-frequency load shedding device, a problem that also needs attention is that when a system suffers from severe active power shortage at the low-frequency load shedding device, malfunctions, failing to start to cut off part of the load, it may lead to the collapse of the entire system. To prevent the plant from collapsing, in such a case, we also need to consider installing low-frequency automatic shading devices in the plant. Once this situation occurs, some of the units in the power plant will have to be disconnected from the system to supply only the plant, and some important users, to gain more deeper understanding of the principle of automatic low-frequency load shedding device. I will set up an exercise for you to analyze after the class. In this lesson, we mainly learn about the basic requirements of automatic low-frequency load shedding device and specific working principle, as well as analyzing the reasons that cause the device to misoperation and measures that can be taken to prevent misoperation, etc. That's all for today. Thank you.